Hi class. We're going to be continuing with the second lecture on the ideal gas laws. We're not going to go to the end of this chapter. The most important aspects of this chapter are in this section, 9.3. I mean, aside from the fact that we looked at the ideal gas law here, PV equals nRT, we're going to be looking at the applications of that in this one. So here we go. The stoichiometry of gas substances, mixtures, and reactions. Use the ideal gas law to compute gas densities and molar masses, perform stoichiometric calculations involving gaseous substances, state Dalton's law of partial pressures, and use it in calculations involving gaseous mixtures. The second one is especially important because if you recall, up here we have PV equals nRT. This can be rearranged as PV divided by RT is equal to N, the number of moles. So we're getting many different ways to calculate the number of moles. If we're given grams of a substance, you divide by the molecular weight. If you're given the molarity of a substance, you multiply by the volume. And in this case, if we've got the pressure, the volume, and the temperature, we multiply the pressure times the volume divided by the temperature, also divided by R, the ideal gas law, to get N. So there's some consistency here. We're all trying to get at the currency of chemistry, the number of moles. Okay. So what's done here is that we're going to rearrange the ideal gas law in order to determine the density, to determine the molecular weight or density of a gas. So density is mass per volume. And so grams divided by the molecular weight here, the capital M here is molecular weight. This is the number of moles. So the pressure times the volume times the number of moles times RT. If we substitute the density into the equation, we get the density is equal to the molecular weight times P divided by RT. Note, we can also turn this around to be RT times the density divided by pressure is equal to the molecular weight. That is called the RAST. That is it's a method for determining, standard method for determining molecular weight. That's not RAST, that's the Dumas method. Recall that density is an intensive property. It does not depend on the amount of substance. But the density of a gas does depend on the pressure, the temperature, and the molar mass. Those are also intensive properties, each one of them. Recall the molar mass of a substance is the grams per mole, or the, I would have called it G instead of M, the mass divided by the number of moles. This expression can be rearranged as the number of moles is equal to the mass divided by the molecular weight, and then substituted into the ideal gas equation. PV equals the mass divided by the molecular weight times RT. And so what they're trying to get at is the density becomes the mass divided by volume. So you multiply by the mass on both sides, and so it appears up here. And the volume can be divided on both sides, so it's going to come down here. So you get mass over volume is equal to density. And so you got P times the molecular weight is equal to the density times RT, which, take my word for it, is the same as that equation. Okay. When a volatile liquid in a flask is heated past its boiling point, it becomes gas and drives air out of the flask. At the temperature of liquid to gas, the boiling point, the flask is filled with volatile liquid gas at the same pressure as the atmosphere. If the flask is then cooled to room temperature, the gas condenses and the mass of the gas that filled the flask is now liquid and can be measured. So this is a representation of the Dumas method of determining the molecular weight of a gas. You then go back to this equation, but rearranged so that you're solving for the molecular weight. You get the density from the volume of the flask. You get the density from the volume of the flask and the mass that was left in it, and you multiply it times the boiling point at which it filled the flask times R, and divide by the atmospheric pressure that you had during the experiment. Let's go back. This is where the gas was weighed by difference. Here's the dry weight, and this is the weight after after the fluid has recondensed in it. Let's see, how much has it gained? Ooh, this looks less than that. This must be the final weight. Anyway, that's the Dumas method for determining molecular weight. The ideal gas law also applies to mixtures of gases if the gases don't react with each other. So this is a mixture of gases like our atmosphere. We've got the pressure total, 760 millimeters of mercury. And this might be the pressure of nitrogen, which makes up 80% of the atmosphere on a molar basis. This is the pressure of oxygen, which makes up about, let's say, just so that everything adds up, let's call it 19% on a molar basis. And this is pretty much all the other gases, but the major other gas in our atmosphere, other than nitrogen and oxygen, is argon at a level of about 1%. And now you got carbon dioxide at 400 parts per million. You've got the vapor pressure of water, which is going to be comparable to that. So, but these three gases, nitrogen, oxygen, and argon, make up most of our atmosphere. And the pressure of each is independent, and the total pressure of the atmosphere is the sum of the partial pressures of each. So that's the law, Dalton's law of partial pressures. The total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the component gases. And so since nitrogen is 80% of our atmosphere, 80% times 760, go back, escape. Let's pull up the calculator, Windows Accessories, calculator. 760, that's the standard pressure at atmosphere at sea level times 80%, which is 0.80, 608 millimeters of mercury is therefore the partial pressure of nitrogen in millimeters of mercury at sea level. Okay, next. Boom, boom. For a mixture of gases A, B, and C, PT is the total pressure of the gas mixture, PA is the partial pressure of gas A, PB is the partial pressure of gas B, PC is the partial pressure of gas C. The pressure exerted by each individual gas in a mixture is called its partial pressure. The partial pressure is equal to the pressure that gas would exert if it were by itself. So here we've got 300 kilopascals of gas A, 600 kilopascals of gas B, 450 kilopascals of gas C. And if we mix them all together, we've got 1350 kilopascals of a mixture. Here's the thing, is that if you are talking about the reactivity of oxygen or the reactivity of something else, it's like the astronauts. Human beings need approximately, well, we feel comfortable with 5 pounds per square inch of oxygen. Our atmosphere has about 15 pounds per square inch of total gas pressure. So, did I say 5? Let's see. Yeah, it would be 3 pounds per square inch of oxygen is what humans are comfortable with. The NASA, because they didn't want the stress on their spaceships, on their space capsule, when they sent the astronauts up, didn't want to put the whole atmosphere in there, the nitrogen and the argon. They just put in the oxygen, the 3 pounds per square inch of oxygen, pure oxygen, and the astronauts were comfortable breathing that. There was a little bit of a problem, well, more than a little bit of a problem. By using pure oxygen, it also made things much more flammable. And the first Apollo spacecraft burned up on the launch pad, Apollo 1, and killing the 3 astronauts involved because it was pure oxygen. So they backed off that a little bit so that it was, maybe 4. They put in a little bit of nitrogen, 4 psi, instead of just 3 psi of pure oxygen. And that made the atmosphere a little less flammable. And then they also made sure the wires and the things the astronauts wore were not flammable to could prevent catastrophe from happening in the future. But, okay, so a gas will behave, its reactivity, for all intents and purposes, is dependent on its partial pressure, whether the other gases are present or not. Okay, we can express the partial pressure of a gas in a mixture in terms of its mole fraction. Consider a mixture of gases A and B. So this would be your 15 pounds per square inch. Oxygen is present at a 0.2 or a 1/5 mole fraction in the air. And so 1/5 of 15 psi is 3 psi. And similarly, nitrogen is at an 80%. So 0.8 times the 15 psi would give 12 pounds per square inch for the partial pressure of nitrogen in our atmosphere. The mole fraction of a gas is the number of moles of the gas divided by the total number of moles of the gas in the mixture. And when we talk about the percent of oxygen and nitrogen in the atmosphere, we're talking mole fraction. It's just the convention that's used for gases. A common way to collect and quantify a gas produced in a chemical reaction is to capture the gas in an inverted bottle that has been filled with water. The volume of gas displaced can then be related back to the amount of gas produced. As the gas travels through the water, it picks up water vapor, H2O, gas. The collected gas mixture has a total pressure equal to the atmospheric pressure. When a reaction produces a gas that's collected above water, the trapped gas is a mixture of the gas produced by the reaction and water vapor. If the collected flask is appropriately positioned to equalize the water levels both within and outside the flask, the pressure of the trapped gas in the mixture will equal the atmospheric pressure outside the flask. We've referred to gas collected over water as a wet gas mixture. Say, for example, the gas being collected was H2, hydrogen. Then the total pressure is equal to the pressure of water plus the pressure of H2. PT is the atmospheric pressure, pH2 is the partial pressure of the hydrogen collected, and pH2O is the vapor pressure of water. So the partial pressure of water and the vapor pressure of water are well, they're not exactly the same, because the vapor pressure of water is what the partial pressure of water is when it's intimately in contact with water. You can have less than the vapor pressure of water in the air, and you call that fraction of the vapor pressure, you call that the relative humidity. The vapor pressure of water, the pressure exerted by water vapor in equilibrium with the liquid water in a closed container. So the key word here is equilibrium, which means that it's as wet as it will get. If it's at any greater pressure, it will precipitate out. If it's at any lower partial pressure, more water will evaporate from the surface. It is an intensive property. It does not depend on the amount of water, and it is temperature dependent. So a higher temperature gives you a higher vapor pressure of water. And here it is. They don't. This is the. This is in. This is in millimeters of mercury. So at 100 degrees C, the vapor pressure of water is 760 millimeters of mercury. That is the same as the atmospheric pressure. And that's the reason why water boils, is that the gas is finally escaping the water and displacing the atmospheric air, because its vapor pressure has finally gotten to be greater than 1 atmosphere, than the pressure of the atmosphere pushing upon it. So what's interesting here is that the vapor pressure of water is actually quite substantial at 40 degrees C, if this curve is correct. This looks like it's 100, it looks like it's 50, actually more, about 75 torr, 75 millimeters of mercury at 40 degrees C. And that's about 1/10. Yeah, that's 1/10 the total pressure of the atmosphere. So the So the vapor pressure of water at 40 degrees C, which is a very hot day, could displace as much as 1/10 of the atmosphere. In fact, it's going to be, the water vapor is going to be more in the atmosphere than argon, which is 1% of the atmosphere. So this is 10% of the atmosphere. Very interesting. Gases may appear as reactants or products in a chemical reaction. The ideal gas law and a balanced chemical equation can be used to relate P, V, T, N in grams of a gas that take part in a chemical reaction. So this is what I was saying at the beginning, is that this is another way of calculating number of moles. Stoichiometric factors can be used to relate the moles of one substance to the moles of any other substance in a balanced chemical equation. This is what I call moles are the currency of chemistry. The volume ratio of any two gases in a reaction at constant temperature and pressure is the same as the stoichiometric ratio in a balanced chemical equation. Okay, what this is basically saying is that the volume of gas is actually proportional to the number of moles of the gas if the gases are at the same temperature and pressure. And this, by the way, was what was called Avogadro's law. And so the classic example of this is that if you generate hydrogen and oxygen by electrolysis, you'll get about twice the amount of hydrogen gas than you get oxygen gas, and it indicates the stoichiometric ratio in the balanced chemical equation. That is, that you're producing twice as much, twice the number of moles of hydrogen gas as oxygen gas. Recall that volume is proportional to the number of moles. Okay, that is Avogadro's law. One volume of N2 combines with 3 volumes of H2 to form 2 volumes of ammonia. Okay, this is just saying that, in fact, this is how we suspected that the atomic theory was correct, was because of these volumes in chemical reactions that occurred. Okay, they're changing the topic a little bit here, but since we're talking about gases, one of the most important issues is the greenhouse effect, the fact that the Earth is not as cold as outer space, especially at nighttime. That's the greenhouse effect, and we absolutely need it and cannot live without it. But the alternative thing here is that we're changing the greenhouse effect with time, with adding carbon dioxide to the atmosphere, and that is causing what's called global warming or climate change. And that could be a very serious problem within our lifetimes. So greenhouse gases trap enough of the sun's energy to make the planet habitable. This is known as the greenhouse effect. Human activities are increasing greenhouse gas levels, warming the planet and causing more extreme weather events. This is the Keeling curve. Well, at least this is the Keeling curve. And an observatory was set up in Hawaii to analyze the atmosphere for carbon dioxide in the late 1950s. And the scientist involved in this, his name was Keeling, hence it's called the Keeling curve. And every year in the wintertime, just because more of the land masses are in the north than in the south, the carbon dioxide rises because the trees are dead or losing their leaves in the northern hemisphere. And then in the springtime, with everything growing back, the carbon dioxide drops. Hence, we got this undulation. Also, by analyzing the ice in Antarctica, we can go way, way back and determine how much carbon dioxide was in the atmosphere in very ancient times, in this case going back 600,000 years. So the carbon dioxide stayed within a reasonable range, and as of today, it's over 400 parts per million. All of these are cut off at some point, but I'll tell you right now, we're well over 400 parts per million. So CO2 levels were typically 200 to 300 parts per million, with a steep, unprecedented increase over the past 50 years. Also, long time we've been looking for the signature in the weather changes, and we didn't start seeing that until after about 1990. We began seeing changes in the Arctic and record-setting high temperatures in the summer. Susan Solomon's research focused on climate change and has been instrumental in determining the cause of the ozone hole over Antarctica. Now, don't confuse that with the global climate change. The ozone hole over Antarctica was because of the release of freons from refrigeration. Also, the person who first noticed this, his name was Sherwood Rowland. I've met him. And he determined that there should be a hole based on the fate of freon, and then using the government's satellite data was able to show that there was in fact a hole over Antarctica, but that data had been ignored by the government because they thought it was wrong. Okay, that's it. Talk to you later. Bye-bye.